And we move to the next talk by Professor Arata Yamamoto.
Yes.
Arata, are you here?
Yes.
Yes. Could you please share your screen, your slide? Yes. Could you please make your slide full screen? Right. Okay, so Arata will talk about the rotation on lattice. Yeah, please.
Okay, thank you very much. Hello, everyone. I'd like to discuss lattice simulation with rotation. Maybe next speaker, Professor Grabta, will talk about their simulation results. So here I'd like to focus on more formal aspect, the theoretical formulation and its problem. Let's start with the analogy to magnetic field. People say magnetic field and the rotation are very similar. Of course, this is correct, I agree. But from the viewpoint of simulation, the difference is also important. I think the lattice QCD with external magnetic field is very established field, but lattice QCD with rotation is not yet well studied. The difference between these two concepts is very essential to understand why lattice QCD with rotation is difficult. First, the similarity can be understood from many physical phenomena. For example, in superconductors, vortex is induced by magnetic field. Similarly, in superfluid, vortex is induced by rotation. In high-energy physics, there is a very famous similarity about chiral transport. Magnetic field induces chiral magnetic effect, and rotation induces chiral vortical effect. So they seem very similar. But there is a very important difference. Magnetic field couples to charged particle, so it couples to quark and anti-quark, but it does not couple to neutral particle, gluon. So in the case of magnetic field, we have to modify only fermion part. But rotation is independent of the charge of the particle, so we need to modify both of gluon action and fermion action. This is one important difference, and there is another difference. Basically, magnetic field is independent of coordinate. We can consider homogeneous magnetic field, and also we can take infinite volume. So if the volume is large enough, the simulation result will be independent of boundary and its volume. But in rotating system, the system is completely inhomogeneous because there is a center of the rotation. Also, Kazuya pointed out the importance of a boundary. Also in the simulation, lattice simulation, the existence of a boundary is very important. A boundary breaks homogeneity of the system. There are two basic strategies for the lattice simulation of rotation. The first one, naive one, is to rotate particles. But this is very difficult in practice because in quantum field theory, there are so many particles, even in vacuum. There are many quark and anti-quark pair creation and also gluon fluctuate. So it's difficult to simulate the rotating particles. Instead of this description, we should choose rotating frame formalism. We should rotate the reference frame instead of to rotate the particles. If the system is rotating in the opposite direction, this description is equivalent to the original description. In this frame, particles are not moving, so simulation is much easier than the original description. This is the advantage of rotating frame formalism. There are two kinds of rotations, a non-relativistic rotation and a relativistic rotation, depending on the rotational speed. Of course, in high energy physics, we are mainly interested in relativistic rotation because they are it is relevant for rotating QGP or rotating nuclear neutron stars. But before talking about relativistic rotation, I will talk about non-relativistic rotation as warming up. In non-relativistic system, rotation is very easy. As you know, it just shift of the Hamiltonian or shift of Euclidean action. The total action will be given by the original action minus angular velocity times angular momentum. This is all. So it's very easy. For example, this is the action of non-relativistic Bose gas. This equation is the angular momentum of Bose gas. This is positive number. This is positive real number. So its simulation has no difficulty. This is very easy. Actually, in this system, there is another difficulty. The time derivative is linear in non-relativistic system, so this part is complex. But this is not the problem of rotation. This part already exists in rest frame. So the rotation does not cause additional problem in non-relativistic system. Actually, this sign problem is not so severe in non-relativistic system. In non-relativistic system, the number of degrees of freedom is small, so we can directly tackle this sign problem, for example, by complex Langevin simulation. We studied this system rotating both gas by complex Langevin simulation and analyzed the vortex property of ultra-cold atomic gas. This is a case of non-relativistic system. On the other hand, in relativistic system, the rotation is not so simple. The rotating frame in relativity should be formulated as curved space with a metric tensor. So we need lattice, the formulation of lattice QCD in curved space-time. We already know QCD action in the curved space-time, so we just discretize the action. For example, this is Dirac-Fermion action in rotating frame in the continuum. These are rotation-dependent part. For example, we can discretize this Dirac-Fermion action by Wilson-Fermion formalism. This is Wilson-Fermion action. We have rotation-dependent terms. They seem very difficult, but anyway, formally, we can discretize the action and formulate lattice QCD in a rotating frame. Using this action, we can analyze physical phenomena, many rotation-induced physical phenomena. For example, this is one simulation result of chiral vertical effect. In this case, this is not QCD. This is non-interacting Dirac fermion. This is vector current, and this is actual vector current of chiral vertical effect. As you know, the analytical formula, the famous formula is independent of coordinate because this is obtained by linear response theory. But in the numerical simulation, the obtained currents dependent on they depend on coordinate. This is xy coordinate, and there is rotation, center of the rotation here. Sorry. Anyway, in free case, we can do everything, but in interacting case in QCD, situation is more severe. There are many open problems. As far as I know, there are two open problems in interacting theories: sign problem and renormalization. The first one is the sign problem. Again, this is Wilson fermion in a rotating frame. These are rotation-dependent part. They breaks so-called gamma 5 Hermitian property of the Dirac matrix. The gamma 5 Hermitian property is important for positivity of fermion determinant, but these terms break this property. So as a result, fermion action is complex. Fermion determinant is complex. This causes the sign problem. And this is gluon action in a rotating frame. Gluon action is more complicated. We have so many terms, very complicated. I will not show the lattice action because it is much more complicated, but basically discretization is very easy. The conventional term can be discretized by bracket, and new term, this term is how to say cross term. For example, fxy times fy tau. It can be discretized by this kind of exotic loop. It is called the chair type loop. The action is complicated, but we can write down the explicit form. The important part is this part. This is complex. So this part, the gluon action also causes the sign problem. So in rotating frame, both of gluon action and fermion action are complex. So this causes the sign problem. This situation is similar to the chemical potential, chemical potential. But in the case of chemical potential, only the fermion action is complex. Gluon action is not modified by chemical potential. The calculation of a rotating system is much more difficult than the chemical potential, than finite density simulation. In our study, we introduced the same strategy as the the chemical potential. In the case of chemical potential, the trick is known, so-called imaginary chemical potential. If you consider, if you transform real chemical potential to imaginary chemical potential to imaginary, the resultant fermion action is real. Of course, imaginary chemical potential is not physical, so eventually we need analytic continuation or the extrapolation to real chemical potential region. But anyway, we can know the information around small real chemical potential. We can do the same thing in the rotating frame formalism. We consider imaginary rotation. We call this Euclidean rotation because this imaginary rotation corresponds to rotation in Euclidean time. Introducing this Euclidean rotation, we can make both of fermion action and gluon action real. So we have no sign problem here. Of course, we need analytic continuation after the simulation. But anyway, some simulation becomes possible. The second problem is renormalization problem. In the standard lattice QCD, we consider homogeneous lattice with constant coordinate independent lattice spacing. So the resultant theory has constant renormalization. Renormalization constant is independent of coordinate. This coordinate independence is protected by the translational symmetry, Lorentz symmetry in the continuum. But in the curved space time, the Lorentz symmetry does not exist. Translational symmetry is broken by the coordinate dependent lattice spacing. Even if we use constant lattice spacing at the classical level, the coordinate dependent metric tensor breaks translational invariance. So the Lorentz symmetry does not recover in the continuum limit. As a result, the renormalization constant is not constant. It is a function of coordinate. So in general, this renormalization constant is very difficult to calculate. I'd like to show one concrete example. Now, please forget rotation. Please consider just coordinate transformation from Cartesian coordinate to polar coordinate. In Cartesian coordinate, we can fix lattice spacing. This is just constant. But in polar coordinate, if you fix the lattice constant in the radial direction, the lattice spacing in angular direction depends on coordinate or depends on radius. We can do the simulation in polar coordinate and the Cartesian coordinate. We explicitly did the simulation in lattice 5-4 theory. We calculated dimensionless combination, dimensionless ratio of condensate squared to the fluctuation. This is a numerical result. This quantity is called condensate fluctuation. This is condensate fraction as a function of radius. Of course, in Cartesian coordinate, this is constant. There is no special point in space-time, so condensate is flat, independent of radius. But in polar coordinate, it depends on radius. Of course, this is just mathematical transformation, just coordinate transformation. So physics must not change. But a numerical result is completely different. This deviation is result of renormalization, inhomogeneous renormalization. So to estimate this difference, we need complicated calculation of inhomogeneous renormalization. In summary, non-relativistic rotation is easy, but relativistic rotation is very challenging for lattice simulation. The first open problem is a sign problem. We solved this problem by introducing Euclidean rotation. Of course, the sign problem is just a specific problem of Monte Carlo simulation. So we can avoid this problem by, for example, mean field calculation of some model. But the second problem is much more difficult because renormalization is universal for quantum field theory. Honestly speaking, I don't know how to solve this problem, but I guess in small omega limit, we can expand in the power of power series of omega, and we can estimate renormalization constant as a at least the lower orders of omega. But I did not do that. This is just my speculation. This is the end of my talk. Thank you very much.
Well, thank you, Arata, for the interesting talk. If you have a question, please raise your hand. Yes. Yeah, please go ahead. Nugza, please go ahead.
Okay. I have two comments, indeed. First of all, when you have a complex action, you may try to simulate by the real part and the complex part of the exponent of the complex part of action add as a factor to the calculable operator. The second comment is that when you transfer in the polar coordinates, we see that in radial direction, you may use usual discretization with constant step. But in angular, the geometrical relation, it corresponds to Q-discretization, Q-calculus discretization, where the calculus is almost as well developed as usual finite difference calculus. So mathematically, they are all more or less equal. So you have not really technical problem because you just change usual finite difference calculus to the Q-calculus, Q-discretization, or geometric discretization, or Q-quantization in the formation language. Yeah, okay, thank you.
Of course, in this case, radial part is constant, has constant lattice spacing. But of course, at classical level, we can control this lattice spacing because we know analytical form of this lattice spacing. But it does not solve the quantization problem. Because this is dimensionless quantity. So at classical level, this quantity does not suffer from renormalization problem, but the quantum level, there is deviation. This cannot be controlled by usual strategy.
Okay, so is there any other question? On one slide, you showed the chiral-vertical effect on lattice by using on one slide you show the chiral-vertical effect from lattice. Is it it?
Yes. Non-interacting lattice calculation.
By using the frame transformation from the usual frame to the rotating frame.
Yes, rotating frame, yes.
But this is just the frame transformation. If, for example, if we have no chiral-vertical effect in a non-rotating frame, then why should we see the the chiral-vertical effect is a physical current from some vorticity or rotation. Then why should we see a physical current by using just the frame transformation?
This is a frame transformation, yes.
I mean, in one frame, we do not have the physical current. Should we have current? I mean, just by using frame transformation?
But this is the same as an analytical formula. Set up is the same as famous analytical formula. For example, in Dirac equation.
Yes. Yes, but in this analytical formula, I think the rotation is the physical rotation, meaning you are rotating a fluid or a system.
In Dirac equation, we can derive the same equation.
Mm-hmm. Yeah, okay, maybe we can discuss in the discussion session, because I see two other questions.
Okay.
Okay, so Dennis, are you here?
Yes. I wanted to ask about this picture. Which boundary conditions have you used? Because I suppose they can be very important and significantly influence the profile and spatial distribution.
This is an open boundary. Let's say I just cut the lattice. So the result depends on the boundary condition. You are right.
Okay, so okay, so Maxime.
Actually, I would like to answer to you in support Arata, saying that what he does, he rotates on the lattice, but what he does, he introduces the background gravitational field and then fixes temperature. And that fixes the scale. So that's exactly what Kenji said in the first talk. You cannot rotate vacuum. You should rotate always matter or, I mean, plasma temperature. So he rotates, so he just makes this gravitational deformation and then fixes temperature. And that fixes exactly, it's different from just rotating, say, without temperature. If you would consider a system without temperature and without chemical potential, he would get nothing. I think Arata agrees with me. So.
Thank you very much. You are right. Yes.
Different, yeah.
Mm-hmm.
Temperature fixes everything. So just you can see it also analytically. Without temperature, you get nothing. But so it's rotation and fixes temperature. That's all. It's not just going to another frame. You define temperature in rotating frame. So thermal distribution in rotating frame. If you would stand in the just in the laboratory frame, you would not get the temperature distribution. So
okay, so okay, now okay, so which means the frame transformation is actually transform a co-rotating frame with the fluid.
Yes, and fixes temperature in the co-rotating frame. or chemical potential in the rotating frame.
Yes,
That's the
okay.
function.
Which means actually there is a physical rotation even in a non-rotating frame.
Yes.
It's actually rotating in a non-rotating frame.
Yes, yes, yes.
But if you see a G00, then the rotation effect comes from the quadratic order. And so the introduction of the temperature is actually not really incompatible with the rotation, right?
It's not incompatible. No, it's not incompatible.
Yeah, so
it's not incompatible. Yeah, it's fine. It's very nicely compatible. Yeah.
Yes, and so yeah, I agree with you, but your explanation is not the full explanation, right?
Yeah, we don't have so much time. Yeah, exactly.
Yeah, maybe we can go on the discussion in the discussion session.
Yes.
That's a very interesting thing. Okay, then let's thank Arata again for the nice talk. Thank you, Arata.
Thank you very much.